Okay, hello and welcome to the Radical STEM Homework Help Livestream. If you have homework questions in math or science, you can post them here in the chat and we will do our best to help you solve it live. In the meantime, I will be solving just some random problems to pass the time. But, just like it says at the top of the screen, don't hesitate to interrupt, because I would rather solve your problems than my random problems. Okay. Let's start it off with a nice integral. Not sure which one I'm going to do yet, but I'll write that down. This one looks interesting. I'm not sure if we'll get anywhere with it, but it looks challenging enough to be exciting. The integral of x squared times tangent inverse of x. Okay. So, the first thing that jumps out to me is I know the derivative of tangent inverse is 1 over 1 plus x squared. Now, does that help us at all with this integrand? Well, if we did something like letting u equal tangent inverse du dx would be 1 over 1 plus x squared. We'd have du equal to dx over 1 plus x squared, which is not anything that we have in the integrand, so I don't think that would necessarily take us anywhere. Unless this also means that tangent of u is equal to x, and tangent squared of u is equal to x squared, which we do have an x squared. And if x squared is equal to tangent squared, that would be 1 plus tangent squared, or rather, we could say 1 plus tangent squared of u times du is equal to dx. So then, if we plugged all that in, we would have tangent squared times u times 1 plus tangent squared du. That might go somewhere. Okay. So this is telling me there's probably some sine squared plus cosine squared stuff going on. Divide by cosine squared and we get tangent squared plus 1 is equal to secant squared. So this is equal to secant squared of u so tangent squared times secant squared times u. I know the derivative of tangent is secant squared, and the derivative of secant is secant tangent. I'm almost thinking we do another u sub here. Oh no, if I tried to do a u sub using this, like u equals tangent, or you know, some other letter, m equals tangent, we would just be undoing our sub from earlier and we would go right back to our original integral. So let's not consider that one. What about this? Wouldn't want to let u equal secant, or m equal secant of u, because then we would have a secant inverse right here, and that would be really nasty. This is a tough one. Maybe I should stop just looking for substitutions and try to think of something else. I wonder if there's anything we could do with even and odd functions here. Probably not. I think that would mostly be useful if we were doing a definite integral over symmetric boundaries. Then we could do stuff using even and oddness of functions. But I don't think that'll really help us with this indefinite integral. I'm gonna step back and think about a different substitution maybe. Or doing it by parts. Because individually we could integrate either piece of this. And if we do derivatives on the x squared, we could get rid of it altogether. I would need a second to figure out the integral of tangent. So if we did this, we would have something to differentiate, something to integrate, plus minus, differentiate the x squared, get a 2x dx. Integrate the tangent inverse of x dx, get whatever that is. Then we would have x squared times whatever that is, minus the integral of 2x times whatever that is dx. The antiderivative of tangent inverse is not going to be pretty. It will be very bad. So maybe we should think about doing it the other way. Differentiate tangent inverse and integrate x squared. Then we would get 1/3 x cubed tangent inverse of x minus 1/3 times the integral of x cubed dx over 1 plus x squared. This looks maybe a little more manageable. It would be really great if these powers were flipped. I wonder if here we could do anything with a trig substitution. Like if we gonna do this in red. If we here let x equal tangent of theta, dx d theta would be secant squared. So dx would be secant squared d theta. And 1 plus x squared would be 1 plus tangent squared, which would be secant squared of theta on the bottom. So then we would get the integral of x cubed would be tangent cubed over secant squared times secant squared d theta. The secant squareds would cancel out, and we would have the integral of tangent cubed. I don't know the integral of tangent cubed off the top of my head, but I feel like that's something we should be able to do. Let me check my calculus book and see if that's in any of the integration tables. Tangent cubed is 1/2 tangent squared plus natural log of cosine. Okay, yeah. I guess we have it then. So this is, what did I say? 1/2 tangent squared of theta plus natural log of the absolute value of cosine of theta plus c. Then that means our original integral is x cubed over 3 tangent inverse of x minus 1/3 times this stuff. We should go ahead and undo the substitution. So that's 1/2 x squared plus natural log of. Okay, so right here, if x is the tangent, it's the opposite over the adjacent. So theta tangent is opposite over adjacent, and then the hypotenuse is x squared plus 1, or the square root of that. So cosine of theta would be adjacent over hypotenuse. So this would be 1 over the square root of x squared plus 1, or x squared plus 1 to the negative 1/2 power. But with the natural log, we can bring that negative 1/2 out front and have x squared plus 1 inside. Yeah, that should be right. So then we'll have minus 1/3 times 1/2, 1/6 of x squared, minus negative, this will be positive 1/6, natural log of the absolute value of x squared plus 1, and our constant of integration. That was a good integral. Yeah, I feel real happy about that one. Okay, let me look around and look for a different type of problem. Okay, this should be a good one. We're going to do some physics. Some physics that I definitely was interested in my first year at college, because I did a whole research project about black holes, and this is about black holes. It's not, I mean, it's a complicated question, but the problem statement is pretty simple. Find the, let me make sure I spell this right. Schwarzschild radius for a star of mass m. Is that right? For which, so this is the radius at which not even light from the star can escape. Determine the Schwarzschild radius of the Sun and the mean mass density it would have to have if its mass were contained in the corresponding spherical volume. Find density for our solar mass. That's the symbol for that. Oh, excuse me. I had to turn off the mic for a sneeze. Find the mass density for our solar mass in its, I'm just going to call it SCH radius. Okay. So, I think I have an idea of how to do this. So this should be based on the speed of light, obviously. Also, I'm gonna draw a diagram and think it out first, partially to explain it, and also to just get myself thinking about the mechanics of it. So we could have a whole star, and then we'll say at the end of its lifetime it collapses into a black hole. So this black hole has a certain radius around it, r, and once you're inside there, even if you're going the speed of light away from the black hole, you cannot get away. So if you are here moving at the speed of light, you'll get away. If you're here moving at the speed of light, you're gonna move inward no matter what. Once you get this close to the black hole, the force of it pulling on you is so immense that it will even accelerate you the opposite direction if you're going the speed of light this way. So we could look at the sum of the forces in the radial direction. And that will be equal to MA. Will it though? Because light doesn't have mass. Maybe we'll just leave that as a variable. We'll see what happens if we just go with it. And if outward is positive, inward is negative, then we want this to be less than 0. And we'll say the only force on us is, like, we'll say we have speed, we're moving at the speed of light already in this direction, but we don't have anything like propelling us. So the only force on us is the force of gravity pulling in the negative direction. So that would be G, the mass of the black hole, the mass of our whatever we are, over the radius squared equal to ma, and being less than 0. And these are all positive numbers, so we would need a negative sign on there. So I think we can cancel this out and then get rid of this intermediate stage and just have negative gm over r squared less than 0. But that doesn't really give us anything that we can solve. Like, we could add it to the other side and have 0 is less than positive this. But all that's really telling us then is these three numbers together do not equal 0. I don't think this is quite the right way to go. Okay. I think we should think about the escape velocity. Because the escape velocity is based on the mass of the body that you are around, and your velocity, which we're interested in the escape velocity being greater than the speed of light. Okay, yeah. So let's see here. So we have a formula for the escape velocity. So here, of course, we have the gravity constant, we have the mass of the body that we're around, and this is the distance away from the body that we are. So, actually I'm going to rewrite that over here so I can have the middle to work with stuff. So if the escape velocity is right at the speed of light, we should be exactly at the Schwarzschild radius. If we're any less than that, then the escape velocity will be higher than the speed of light. And if we're out here, then the escape velocity is less than the speed of light, so we can get away regardless. So this should be true for the radius that we want to find. So then that gives us speed of light squared equals 2gm over r, and r equals 2gm over c squared. Dividing by c squared makes this a very small number, depending on how big the mass is. So let's see. The gravity constant, let me look up what that value is again. .67 times 10 to the minus 11. The speed of light is 3 times 10 to the 8th meters per second. I guess I should write down the units for this. Newtons times meters squared times kilograms squared. So this will be m times 2 times 6.67 divided by, I'll say 3 squared. Then we have 10 to the 8th times 2, so 10 to the 16th on the bottom, and a 10 to the negative 11 on top, which would be 10 to the positive 11 on the bottom. That's going to be m times 1.48 times 10 to the negative 27th meters. So unless the mass of our body is really, really big, this is going to be a remarkably small radius. So for the mass of an entire star, you would have to compact it into something extremely small, like a black hole, for the escape velocity to be at the speed of light. Okay, let's take this now and do some calculations about our sun. Okay, so we did the first part. Now find the mass density for our sun if it was all contained inside of its Schwarzschild radius. So that mass density is going to be the mass of our sun divided by the volume at the Schwarzschild radius. I guess I'll denote that RS. That's going to be the mass of the sun inside of 4/3 pi r cubed. Yeah. Except this is the Schwarzschild radius. So it's going to equal 3/4 pi is still on the bottom. When we substitute in for RS, we're going to put the mass of the sun there. So m of the sun cubed times 1.48 times 10 to the minus 27 cubed with the mass of the sun on top. And this is going to be an absurdly small volume. So let's look up the mass of the sun. It is... oh, interesting. That's a strange definition there that Google gave me. Okay. The mass of the sun is about 2 times 10 to the 30th kilograms. This will be 3 over 4 pi times 2 squared, because this one will cancel that and make it a squared, times 1.48 cubed, and then we'll have, oh my goodness, this is going to be so small, 10 to the negative 27 times 3, and from the mass of the sun we'll have, oh, if that's negative it'll go to the top, okay, 10 to the 27 times 3, and from this we'll have 10 to the 30th times 2 on the bottom. So 4 times pi times another 4 times 1.48 to the third power. That's 162.95, so I'm just going to round it to 163. And I'm going to have to calculate that too. 27 times 3 is 81, 30 times 2 is 60, 81 minus 60 would be 21, so times 10 to the 21 kilograms per meter squared. Okay, yeah, that makes sense. So I was right that this was a very small volume, which is precisely why this is such a huge density, because we were dividing by that very small volume. And yeah, that is an insanely huge number. Okay, that was fun, doing some physics. Okay. I think I see an integral calling my name. Actually, there's maybe a couple that are calling my name. I'm gonna save one of them for if I can't solve the other one and I need to come back to it. So first we'll try the hard one. So we have the square root of x over 1 plus x. Okay. What if we let u squared equal x? Or in other words, u equal the square root of x. Then du dx would be 1/2 x to the negative 1/2. Bring the dx over, bring that 2 over. That's also x to the positive 1/2 on this side. But x to the 1/2 is just u. Oop. So dx would equal 2 times u du. So we would have u on top. We'd have 1 plus u squared, and then dx would give us 2u du. So overall we would get 2 times the integral of u squared over 1 plus u squared du. Okay. Does that put us in a better place? If we did this by parts, we could integrate we could integrate du over 1 plus u squared as tangent inverse of u, but then that would end up in our following integral, which would not be fun. We might be able to do another trig substitution because my mind always goes to those. 1 plus u squared, if u was tangent, that could become a secant squared. We'd have tangent squared over secant squared. Let's see, if tangent is, I'm just going to write this out sort of generally. Tangent is sine over cosine squared, and secant is 1 over cosine squared. Then that would just be sine squared. And that should be an integral that we can do from a table or from memory. Yeah, I think that's our way. So another substitution will let u equal the tangent of theta, then I forgot about the du. du d theta would be secant squared theta. Bring the d theta over. So we would get 2 times the integral of tangent squared on top from the u squared, 1 plus tangent squared equals secant squared, so we would have secant squared on the bottom, du becomes secant squared d theta, so the secant squareds cancel and we have the integral of tangent squared, which I believe is another one that we can get from a table. Yep, tangent squared is tangent of u minus u. Gonna like make a line there that shows the difference between the substitutions. And say that our original integral equals this each time. So then that equals 2 times, what did I say? Tangent of theta minus theta plus c. There should be a 2 there as well, because it's 2 times tangent minus theta. Then we need to undo theta and go another step back and undo u. So tangent theta is just going to be u. Theta will be tangent inverse of u. Oh, tangent inverse did show up. U will just be the square root of x. So this will be tangent inverse of the square root of x. Okay. So our original integral is 2 times the square root of x minus 2 times tangent inverse of, go ahead and erase all that stuff. Tangent inverse of the square root of x plus c. That was another good one. All right. Okay, I think we'll end off with one more, the easy one that I was saving. Easy. I don't know for sure, but it looked like it wasn't going to be too crazy. So we have cosine of theta times the square root of 4 minus sine squared of theta d theta. This looks like it should be a pretty standard trig substitution. Maybe not even a substitution. Well, maybe. Since that's a 4, that's a little strange lemmatic. Because since sine squared plus cosine squared equals 1, then that means 1 minus sine squared equals cosine squared. But that is not 4. and we have 4 minus sine squared. If we could somehow transform this, then we'd be able to get cosine of something squared inside of a square root, so it undoes itself. So I know if we have like 4 minus x squared, you can let u equal 2 times sine and get exactly what you want, because then you can factor out the 4. But can we substitute this with a different trig function? What if we let sine of theta equal 2 times the sine of some new variable phi? Then sine squared would be 4 sine squared of phi, and then we could factor that out and we get 1 minus sine squared of phi inside of here. But how would this play out? Oh, I don't think it's going to be pretty, because if we, how would we even do that? If we try to get our d theta d phi relationship, like, you know, somehow get d theta d phi, it's gonna be ugly. I might have misjudged which integral was easy and which one was not. So like, theta will equal sine inverse of 2 times the sine of phi. So then d theta d phi would equal the derivative of sine inverse, which I don't know off the top of my head, but I'm sure it's not pretty. Derivative arc sine, that is 1 over the square root of 1 minus the argument squared, so 2 squared sine squared of phi, and then the chain rule says we take the derivative of the inside, so we would have 2 times the derivative of sine is cosine of phi d phi. So, oh no, oh no. So inside of here we would, I don't think this is going to work, but I'm just going to see what happens if we plug in the pieces. I'm pretty sure it will be absurd. For one, we don't really have anything that we can do with the cosine of theta. I was kind of hoping somehow through this substitution it would be absorbed, but it is not. If we have theta here, sine is opposite over hypotenuse, so 2 sine phi, 1 square root of 1 plus 2 squared sine squared phi. So cosine would be 1 over that radical. Oh no. then we would have the 4 will come out of that, and we'll have the square root of cosine of phi. So square root of cosine squared of phi, so it will be cosine of phi. So that's these two pieces so far. Then d theta will be this monster, 2 times cosine of phi over the square root of 1 minus 2 squared sine squared phi d phi. So we could bring these constants out front, have an 8. We could combine those two cosines into a cosine squared of phi. We could put these under the same square root and multiply them out. We'd have a square root of 1. Let's see. We would get, minus 4 sine squared of phi plus 4 sine squared of phi minus 2 to the 4th sine to the 4th of phi. So those middle terms cancel out. d phi, okay. So it's simplified to a lot smaller than I thought it was going to be. Still does not look pretty or like anything. Oh, camera went weird. Or like anything we're going to be able to solve in this form. We are at the end of our hour for the live stream. So I think we're just going to leave it at that. Maybe we'll solve this one next time, maybe not. Anyhow, if you have been watching, thank you for tuning in to the Homework Help live stream. And hopefully next time you will have homework questions to ask us, because it's more fun to help you solve your homework problems than to work on mine. So until next time, have a radical day.